Welcome everyone to our Chesapeake Technology Workshop. Today we're working on the bathymetry processing tools. I'm Harold Orlinsky. I'm General Manager of Chesapeake Technology. And with our team here, we produced a lot of new features for our bathy processing. Some have been out recently, some have been out in the past, so we've done some additional work on. So I'd like to spend 30 to 40 minutes on showing off some of the tools that we have and some of the things we could do. So let's start. We decided a couple of weeks ago to do our morning sessions with the Coffee with Chesapeake. It allows us to give you a little bit of side scan bathymetry and sub-bottom, not going into every detail of the program, but to show off some of the things that we could do. I hope you enjoy this session, and if you have any questions, certainly comment into the questionnaire on the GoToMeeting, and our support team of David and Patrick will answer those. Those that we can't get to, we'll send you an email. So let's get started. So we talk about calibrating your system from a patch test to a beam performance test. You know, we ask these questions. Why do we do it? How often should it be done? And certainly, how does it work in Chesapeake Sonar Whiz? Other programs do it. They do it the same. They do it differently. So we're going to see how does it work in the Chesapeake Sonar Whiz. We'll cover these questions and more with your multi-beam data. I start out with a cute little tip. We say that not every day goes planned. And certainly for this guy, it's not going well. But in the survey world, we make a few of these calibration checks, and we can end up getting a decent result. We all know that we spend $100,000 or more on a multi-beam system, and this is real data that I collected. And when we come off the boat after a few hours and we went through processing, and the data looks like this, and the client wasn't very happy. It's like, what happened to the data? And in a relatively short amount of time, we did some processing, we did a calibration, and this was the end result. It's the same exact data, but notice, a 3.5 and a 1.7 degree roll and a pitch error make a huge difference. In terms of absolute, if we look at the multi-beam patch test, it's the wide swath multi-beam systems are great for the coverage, but as we go further and further out, the errors, get exaggerated. Shallow water, we don't see it as much. In deep water, we're talking 20, 30, 40 meters, we're going to see problems in the data. In 15 meters of water, in a 1 degree error in 15 meters of water, you'll see a 1 meter depth error, 1 meter horizontal shift. So that part of the components it's a position error and a depth error that we have to be careful of. So we ask our questions. Well, I measured my boat offsets. You certainly did. You did it with a tape measure, you did it with a laser, but it's not good enough. It can't be as precise as what we're trying to do. We're trying to get the installation offsets between a motion sensor and the multi-beam, and for latency, it's for the positioning system. But we're going to use the bottom. We're going to say, okay, here's our bottom as a reference surface, and we're going to go through a lot of iterations. So it's not just one pass, but what does a roll area look like? And we can look at our lines and A to B and B to A, put the lines on a flat area to come up with some kind of solution for roll. We look at our pitch and our yaw. We need features or a slope. And I'll go through two examples today with using both. And sometimes features are better and slopes don't work because of positioning, but we'll see how they work today. I say run tests in deep water, and I will prove a point that the shallow water pitch test won't work. And you'll see why, because the GPS error is going to be greater than the error we're trying to find. So when we do a patch test, and like I said, we're going to go through the example in the program, but I wanted to make sure that there's a few hints and ideas that you have to keep in mind when you run a patch test. If we look at the example on the left, the bathy, it's two lines, reciprocal lines, a bunch of rocks, but we could probably find a section across that's pretty flat in between the rocks. But if we take a look at the image on the right, the problem is on the right, we're doing a standard deviation. I don't want to cut a line across that's potentially has a lot of noise. So if we look at our slice, we can say there's our section for our roll line. There's not a whole lot of deviation. But if I only looked at the color map and I cut across down there, we'd probably say, well, there's an area of noise. Now, this one's probably a little bit more of a prominent because maybe you see a rock or something goes on. But if we color code the data as a standard deviation, we will get a better chance of removing invalid data. The question goes now, do we process our data before we run the patch test? You should. It's not necessary, but the problem is if we're doing a patch test for roll and all of a sudden there's a lot of noise and flies in the data, some of that will take into account. So yes, you should do some processing prior to doing a patch test. So let's take this Sonar Wiz patch test in action. Oops. There we go. Here is our data. And this is what our data looks like after we run a patch test. It's just night and day difference. And all we did was run it through the one-ish roll and pitch and yaw. The latency value nowadays are not very prominent because of the precise timing and network communication, but the tests are the same in terms of using data on the bottom to parallel lines, the same lines. In the case of a latency test, it's lines with different speeds. But we're going to go from a data set like this to a data set like this. And if we look at our bathymetry itself, we have this many lines. And the story goes over here is that we're running a test pattern. And we went up and down on the first line. It's like, okay, well, there's a lot of areas out here for flat. The boat driver was going offline a little bit. We had to get a little bit better. And so we did a second pair of lines a little bit further in, and we came down and we see, oh, look, there's a rock. That's a perfect example for a pitch test. And that's why we stopped the reciprocal lines. And then we finished the survey later on that day, and we noticed there's a huge boulder field, which would have been a whole lot easier and better for pitch tests. So that's why we have double lines in the front and not so much in the back. But if we just look at, the second set of lines, it goes up and down, back and forth. There's a flat area, there's a rock out there, and we'll use this for roll and for pitch, and we'll use it later on for the yaw test. I did say, well, let's not just look at the color code, but let's look at a standard deviation. Because we don't want to cut across some areas that have a high uncertainty. Files are enabled in bathymetry. I'll go into my patch test, I select my roll calibration, and I go left click and across. And we cheated a little bit because we started with 3.57. These were the actual results. But if I put back in 0, this is the data we came off the boat with. The automatic patch test, you put a minimum and a maximum. We have no idea what it is, so maybe I'll say -5 degrees to 5 degrees, and I'll use a step of a half a degree. And the steps can be as small as you want, but we're trying to narrow it down. So let's try to do a pretty crude results at a half a degree step, and we're coming up with 3.5 degrees, -3.5. Well, I can zero in a little bit more. I can say -4 to -3 and put it in a tenth of a degree. And you probably don't want to go a lot less than a tenth of a degree because the resolution isn't there. So we're down to 3.4. On the main screen itself, we can show in the settings, we can show the bathy points if we want or not. Sometimes you just want to see the profile. And you can show the thickness of the bathy points if we make them a little bit thicker, if we're going to go like that. Notice there's flies in the data that we didn't account for, but the test ran it itself fine. If we're comfortable with it, we can hit save and it automatically updates in the vessel editor and will be used. But one of the things, this is a training thing. What do we do for the patch test? Is we try not just to take a single line, never take a single line. So this is 3.4 and we'll say, okay, we didn't save anything. I'll go back to my patch test and do my roll calibration and I'll try to cut it across here again, staying away from the hot spots. And I'll start the automatic calibration and I have -3.5. So we do this a few times to come up with our best result. Whatever we want, we can type in there and we can hit save. Similarly, with with the roll test, with the pitch test, let's see the rocks that we're looking for. We're going to look for these rocks out there. The pitch is a little bit more difficult. You just can't randomly pick. You're looking for the feature. So it's a little bit less of finding multiple areas. But in this case, we'll do our pitch and we'll go up and down. And you don't have to do the entire line. We're just looking for the pitch across the rock. We know the rock's not going to move. The pitch angle offset is what's doing it. We'll put in 0 to start. This is what the data originally looked like. You notice a little bit of an offset there. And if I take off the Bathy points, we can show it a little bit better. And that's the issue. And then pitch and latency do look the same, so we have to make sure latency works fine, or is done first. We'll do the automatic calibration, and notice it's taking a little bit longer. Well, I started at 0.2 degrees. I'm going from -5 to 5. So we probably should have gone in and made the step either a larger step or a narrower range. Since we don't know what the values are, we start with the large range and put a large step in, half a degree, even 1 degree to come up with something to start. And that gets a little bit better. We see -2. We also have the slider bar up there where we can slide the values, and I can visually see what would come in. So even though the computer does all the work, we may want to visually say we want to see something differently. And we could do the same thing with the yaw test. We have a line out there and a line out there. We can do a couple of yaw tests as well. But one of the things I also wanted to show is what happens if we didn't have a feature. If we had simply just a slope of data. The test will still work, but we have to be careful with the data. Let me get, sorry. I'll do that in a little bit when we get to the performance test. But when we do this patch test, the slope or the feature, whatever we'd like to see. So I say, well, we're ready to congratulate ourselves. We did a good job. Well, not quite. And here's the problem. Here's where the important part is of learning about the patch test. It doesn't always work. As much as a computer tries to come up with a solution, an automatic solution, it can get confused. If we look at a sand wave analysis, sand waves are features on the bottom, a little bit of a slope, a little bit of a feature, whatever we call it. But here's a case where we have a bunch of sand waves and we want to do a pitch test. Well, the ripples do look the same, and here's the problem. Well, we see there's some kind of adjustment we have to do, and we go into the automated calibration, -4 to +4, whatever we want, and we say automatic calibrate, and we run a pitch test. Patch test for pitch. And it comes up with this first iteration. Notice that this slider goes all the way to the left because it says, I can't find a solution. I'm just going to find it. And we have to run the test again. But it went 4 degrees shifting and it didn't find anything. But it moved everything 4 degrees. So we run the test again. And when we run the test again, it says, okay, well, now at 8 degrees, the peaks are lined up. But here's a problem. I don't think it's 8 degrees. I think it hit a multiple of the sand waves. And here's the problem. The result says 8 degrees, -8 degrees, +8 degrees, whatever it is. We have to be a little bit smarter. Can we look over the side and see the multi-beam? Can we look at the motion sensor? Are we seeing an 8-degree tilt on it? It's probably not. I mean, the program itself can process data 10, 20 degrees. It doesn't really matter. But if it's a huge installation offset of -8 degrees, we might want to fix that just because we have the opportunity to. So don't always take the results as the only thing. Look at the big picture. Remember when I said that the pitch test won't work in shallow water? When we look at our survey world, we say, we do our sound velocity cast in our survey area because we want to know what the water is in our survey area. Well, the patch test doesn't have to be in our survey area. And if you're working in a marina and it's shallow water, try to go offshore. You really want deeper water. And here's the point. If we want to resolve pitch to ½ degree, which is normal, and we're in 3 meters of water, if you do the math, a little trigonometry, we'll say, well, that little feature in the bottom, the seafloor, is going to move 2.5 centimeters. Problem is, we can't find it. Our differential GPS best case scenario is 50 centimeters. We go further on, our RTK system best case could be 3 centimeters. Yeah, I'm sure someone can say it's 2 centimeters, but it doesn't matter. It's the magnitude. It's about 3 centimeters. And we're looking for something that's less than that. And that's the problem. So shallow water testing won't work really well. You'll come up with a result, but because the position uncertainty, things are going to move, and you're just not going to get a valid result. So let's move on to the Sonar with beam performance test. Now, we added this recently in the last month or so, month and a half, and it was one of those things that we need to use or need to show in our data set how well the multi-beam system is. It's not just multi-beam performance test. I call it a beam performance test, but it's an overall system test. If we have an offset in a position offset for the multi-beam, you didn't measure it right, you'll show up as a bias. It won't say your multi-beam is shifted or not in the right offset from the IMU or the offset from the reference point, but you'll see some kind of bias in the system. What we're looking at is left and right, minus 60 degrees to plus 60 degrees is the swath of the data. This is one that with only 120 degrees. We see our blue main line, which is our mean data. Doesn't mean much, but we look at our upper and lower bounds, and that's the uncertainty across the swath. And in this data set, it's actually pretty good. You can see on the right-hand side, it starts to slope up, and you typically see a bit of a smiley face where the ends go higher than the nadir section. But what we're looking at on the big picture is about 10 to 15 centimeter uncertainty across the entire swath, which is actually a really good test. Some of the statistical outputs we have for the beam performance test will show how it meets IHO standards for special order, standard 1, standard 2, number of points in that. So there's a lot more than just a graphical display. So the Sonar with beam performance test, once the alignment between the Sonar and the IMU, the patch test is done, the next part is to prepare the surveys for this beam performance test. Again, we ask the questions, how repeatable is my survey data? How far on the swath is acceptable data? And on the QC side, is there a single beam, not a single beam multi-beam, but a single beam or element, a single beam or two that are misaligned? We can see just prior to the sheet before, we'll have a spreadsheet that comes out and we'll check each point. So there's a lot of output data. And when we go across, we have tens of thousands of points that we're looking. So the test is quick. It might take 15 or 20 seconds. It's not the press a button and go. So we'll see how it looks. A little bit of a setup, and we'll go through this as a real life and as an example. But we get a reference grid. In this case, it was oversampled at the bottom. We were doing some training, so we didn't need this much data. But typically, you want to have a grid, 7 times the water depth, and make the line spacing approximately 1 times your water depth. So in 15 meters of water, you will want to do 15-meter line spacing. The reason being is we're going to clip the data in processing when we make this grid to 45 degrees, and 45 degrees is 1 times your water depth. So we want to oversample the bottom. We want to remove any of the flies. We want to remove any uncertainty. As you get further out after 45 degrees, we fight refraction. We fight physics. We fight a lot of things. Motion sensor, degrades a bit, or errors show up. So the reference surface we build, we will cut out to 45 degrees. If we had we knew the seafloor bottom. We had an XYZ of the seafloor, and we knew that the tide was perfect and it wasn't moving. We wouldn't have to go through this exercise, but we don't. We're going to have to come up with some reference surface that we have to come up with. The line should be collected in different directions. They should, to remove any biases. And then we have our crossing line, our check line. It should go in yet another direction. Don't use one of your lines for your reference surface as your check line, because you're just repeating or you're going to ignore some of the biases. So this independent check line. So this case is a perfect example of lines going in different directions, an orthogonal line that goes in yet a different direction, and we go across. We process the data and we get a nice grid. We can output it out as a 1-by-1 grid. And then we have our crossing line. But since we're working all within the program itself, we don't have to export out an XYZ. We don't have to compare one grid to another grid. All we have to do is enable the grid, enable the main crossing line or the check line, and the performance test will run. But sometimes we have a problem where we don't have a nice reference area. Well, we didn't do the proper reference check, and it was only the thought afterwards, like we should have done it while we're out in the field. Well, here's a case where, okay, I have a lot of up and down lines and one crossing line. Can I make a grid out of that? Certainly you can make a grid. I mean, it's better than nothing. But if we look at this, we have a second line that's a cross line. So we're not using that first crossing line. We're going to get another check line. And from that, we can use our check line across the surface area. Is it the perfect reference area? No, but it gets you something. So it's one of those things that allows you to come up with I call it an almost beam performance test. In fact, I named the project as a wannabe performance check. I just wanted to make sure that, we can see systematically how things go. And we can look at the data, and it actually looks like a performance test. This was the data on the right-hand side of the output. And notice, as I said, on the left side and the right side of the graphical display, that it tends to go up like a smiley face or a frown, depending on if you're looking on the top or the bottom. And in this case, at 65 degrees, it's a 1.5 meter error, uncertainty. We're down below it at 45 or 50 degrees, it's less than 0.5 meter. So this system was one of the earlier multi-beams. This is probably for about 10 years ago, and I'm not sure which one it was, but it was, the systems are getting better, and that's why the performance of that earlier one went straight across at 10 centimeters. Hi, so results of, actually, I'm going to run the program. This was my next slide, Alt print screen. Go into my Sonar Wiz. Give it a second. So there were a total of 3 projects I had. I had the patch test from the Costa Rica project, and I had this performance test, and I had the wannabe performance test. If anyone's interested in this data set, certainly let me know. I can send it to you. But let me take off this one line, which is just hanging out there. It's probably a patch test line. Yep. There's my reference data. And to show how we're clipping the data, let me just take a single line. And if I go into bathymetry, of all the lines I wanted, that's not the one I want. A single line, there's a random line. If I go into bathymetry into my swath editor, what I want to show is that I clip the data to 45 degrees. You can almost see it out there. But in the swath editor, you can see the flagged data points. And the point is, we want to get rid of everything on outside of 45 degrees. If you wanted to use 50 degrees, you can. If you oversampled it more, you can use 35 degrees. But you can see that this data has been deleted out or rejected out. So we have a really tight Bathy grid. And you saw from before, that's what my data looks like. But we don't need to see the data. We're going to go ahead and create a grid from that data. And I went ahead and I created a grid. Remember, don't use your crossing line for your grid. And we're not going to go through the process of creating the grid. Let me take that away. But here is my grid data. I created it to 1 by 1 grid, 1 meter by 1 meter grid. Actually looks pretty nice. We highlight the crossing line that we want. And I'm going to use line number 29. Random line, and you can only use one at a time. You can collect as many as you want. But the way that the test will run is in the Bathy file. Open it up under Performance Utility. It says there's line 29. There's my grid that I chose, 1 meter depth, and we'll say OK. Like I said, we have probably 20,000 samples per beam that we're doing analysis on. This takes probably about 25 to 30 seconds. You can see the progress bar going. The output all goes into into your project under your bathymetry folder, and it says statistics. And we'll look at that once this is complete. Just about done. And the nice thing is, it does do the report in Excel spreadsheet with some graphical displays. If the computer doesn't have Excel, you could still run this test. You end up with a CSV file in that folder in the Bathy/statistics folder. and certainly do whatever you like. So we're done. Automatically open. I'm just going to close down this one dialog box. There's my performance test in my Bathy. So that's what we saw before. As we go further out, it got a little bit worse, but it's still 10 or 11 centimeters. And if we look at this 95% confidence level, that's what we're seeing. We have 4 tabs over. So the first tab is every 5 degrees, we have an increment. You know, general idea of what goes on. Is there a certain section that goes on? Notice that there's almost 20,000 samples that we're looking at each point. So if you have a flyer in the data, again, it's not going to completely throw it out. It'll say the maximum value is out. This is where I say we have to process the cross line. We're not going to do any filters on it, on an angle filter, but we want to process it like we normally would. So if there's flyers in the data, we should certainly get rid of that. The next tab over is your histogram of angle ranges. And we can see if there's any skewness, any bias. But there's a lot of information that goes on here. And unfortunately, I picked a really good data set. But if we look at the special order, you know, the entire swath is accepted at special order. And if we look at order 1 and order 2, you can see the number of points that are going to get rejected. In the next one, we'll see not accepted in some of these. But it shows that this is really, it's not just a good multi-beam and a good multi-beam and a motion sensor, but a good overall system. Again, we have, you know, on the 15-degree histogram or 20 degrees, every 5 degrees, we have a different bit of a histogram and a lot of information that goes with it. And our third bullet is our beam statistics. Beam 1, beam 2. What does each of these beams mean and how are they acting? What are their angles, min, max? What's their difference in number of counts, the standard deviation, the confidence level, upper and lower bound? So if you had one bad beam inside the data set, you could see something doesn't go well or something's not going right. We'll close this out. And if we look up into Tools, into the project folder, in my bathymetry, there's my, I thought it was called statistic, that's performance test. There's my Excel spreadsheets. And that's exactly what we showed a few seconds ago. So if you have Excel on your machine, it automatically opens up. Otherwise, the data gets saved. But we don't always have a performance test. We don't always have a grid. Well, what happens if we have this, the wannabe data set? I actually named it patch test, performance test wannabe. This wasn't a full statistical on the bottom. That's as much as the data as I got. Well, I had to make a decision. I decided that one of the lines I wouldn't be using. Oh, wrong line. It was 1340, missed it by 1. That's the one line I won't use. So I'll take everybody else. I'll process it to 45 degrees. I'll go ahead and I'll grid it at a 1 meter grid. And I create a grid. And now I want to use that, my single line, my 1340. Well, I'm going to have to disable everyone. You only want to have one line in there, so we'll disable everyone. Disable. And I'll load up this one 1340. Is it perfect? No. The performance test says you're supposed to be on a flat bottom with a slope of 3%. Well, I tried to get some, it's a bit of an upslope. Again, it's not perfect, but let's see what happens with this performance test. I run my performance utility, my one crossing line, my depth grid, and I'll say, okay. This one goes a little bit fast. It's not as much data. But it's more of a normal statistical output in terms of outer beams not working really well. And you'll see it in a few seconds. Okay, I think we're done. Sorry, one more scrolling blue-green bar. So the exercise was, we want to do the performance test. We're back in the office. Can we come up with a, some part of the survey area that has, enough of an information reference area and a crossing line that can be used? Now, close out of this. Close. Excel. Open. And there's my typical curve. And this is where I said, the outer beam. So if we say, well, I want to go out to 60 degrees. Well, 60 degrees is a meter uncertainty, 1.75 meters. Maybe at 55 degrees, it's a little bit more than 50 centimeters. Well, what really is the statistical cutoff? Well, if we look at histogram at angles, we go up on top, we can see that we are finally rejecting beams. So for special order with this data set, anything beyond 25 degrees isn't accepted based upon the math that we do. If we look at order 1 and 2, everything is accepted. Order 2 is everything. Everything gets accepted in order 2, unless you're really bad. But this really tells you that, can I be a special order test with this system? And the answer is, if you only use 20 degrees of the data, and that's the problem. It has nothing to do with the wannabe test. Again, it's the setup of the system. It's the system itself. And if we look at beam statistics, you can see the min max. There's a lot of values out there that are more than 1 meter or 2 meters out. Of course, as we get closer to nadir, here's our nadir section down there. There's my nadir section up here. The maximum is 3/4 meter. Sorry. So the results of the beam performance test. We have the graphical visualization of the data. Total number of soundings and min max. Use whatever you need to show or to prove or to disprove the system capabilities. Again, it's a system test more than anything else. The results of the beam performance test, we can check our data against IHO standards. We can count the number of points that failed, not us, but the system will reflect the number of points that failed a certain test and details for each of the beams. So it's a really good test. Like I said, we put it in our 7.6 release in May. We're going to continue to make slight improvements, different graphical displays, but that's how we're going to run our performance test. It's certainly needed for a multi-beam survey. It will work on a interferometry survey, interferometry system, except for the last page. It even says, note that this data is only applicable to multi-beam systems, because there's really no beam numbers in interferometry. But everything else in terms of the graphical displays and swath width will show up. So in my conclusion is that a little work up front will make your survey data look really good. We run these tests at the start of the survey or when things change. And when we say when things change, are you moving the multi-beam? Are you taking it off? Are you putting it back on? If you're running a 2-month project and everything is installed, you don't have to run another patch test. But if you disassemble the boat and remove it, later on, we really should. If you have a retractable mount and you pin it out and the pole goes up and down and the pin holds the system, you probably can get away without running a patch test every day. But as a little sake of sanity, why don't you run the test, the first day or 2 or 3, just a quick little patch test to see if the pole is really holding up. Most of the time it does, as long as you have a nice pin or even a 2-pin connection. I say that the tests don't take a lot of time and they're easy to do. Sometimes you get frustrated because you can't find the feature on the bottom for the patch test, or sometimes the reference area is on a slope and we have to go a little bit further downriver to find a patch find a performance area, reference area. So they don't really take a lot of time once you have the right area, and they're generally easy to do. Once you run through the bathymetry processing, things are just straightforward from there. A few final comments I have is that tomorrow we're going to be posting our 7.6 point update. A couple of weeks ago, we had our 7.6.2 update, or 7.6.1. We never had a 0.2. We just merged everything in our 0.3 update. 50 new updates of features or bug fixes. We listen to the clients, we listen to everyone to give us ideas of what we want to do, and they get included. Ultimately, we're working on 7.7, which is our next main release, but we're going to have these incrementals to keep everyone updated with some of the bug fixes. So if there's any issues with the software, just let us know. I invite everyone to our webinar next week on the 24th. It's our sub-bottom webinar. So like I said, last week we did side scan. This week is bathymetry. Next week is sub-bottom. It's not really a training how to press buttons. It's more of a general what we're trying to do. So with the sub-bottom, it's going to be an interesting, new features that we're working on and some techniques on processing sub-bottom data. And David Finlinson will be doing that one. The webinar is recorded. It'll be posted on the website. If anyone needs or would like a copy of the slide presentation or the data set, just let me know. You just send me an email. And with that, I'd like to thank everyone. And if you have any questions, feel free to ask. Send an email or we'll just give us a call. Thank you.